All right, today we got some important stuff. We're going to learn about the ultimate goal out of this lesson is what's called the first derivative number line. It's one of the more useful tools you'll see in the next couple of weeks. However, the College Board doesn't like them, but I don't care. And I'll explain what that means later on as we go through it. So we're going to start by talking about some increasing and decreasing on a function. Ridiculously simple. We're going to talk about the first derivative test, which will finally allow us to answer the question we've been wondering for many days. Is that critical number a max or a min? The only way we've answered that so far was by looking at graphs. But we can do it without using graphs, using something called the first derivative test. And then your challenge for today is to complement two strangers. No, strangers, not strangers. Okay, so here's some calculus speak for you. Tom, you ready for this? You're going to help us. Whoa, I don't know what just happened. That was weird. Okay, so I'm going to read this to you. Then I'm going to draw a picture, and then you're going to see if it makes sense. Okay, so a function is increasing on an interval if for any two numbers, we call them x1 and x2, if on that interval x1 is always less than x2, but f of x1 is less than f of x2.
I get it.
Okay?
Yes.
What does it mean?
It means that if any two numbers, if any two x values, if one x value is smaller than a second x value, then the y value that goes with the first x value is smaller than the y value that goes with the second y value. If those things are true, then the function is increasing.
Wow, that was an amazingly astute description. I didn't think you'd get that far, so I was going to draw a picture. Tom, is that increasing or decreasing?
It depends.
It's increasing. Why is that increasing? It's going up. It's getting bigger. Does that make sense? Okay, the counterpoint to that would be decreasing. Tom, is that decreasing?
Yes.
Why?
Because the opposite is true.
It's going down. Okay, so there's two parts to a lot of the lesson today. One part is the calculus, that gunk in the rectangle. And the other part is the logic. If you stay with the logic, you'll do just fine. If you get bogged down in all the calculus, it's going to cause some problems. So the question is, why am I giving you the calculus? Well, because at some point, you're going to see a problem that's going to have some calculus speak to it. So what does the calculus speak mean? It says, well, I've got a point over here, x1, and I've got a point over here, x2. x1 is less than x2 because it's to the left of that. But since x1 is less than x2, since f of x1 is less than f of x2, it's lower than x2, so you got to go up, increasing. Same is true over here. I've got x1 over here on the left, I've got x2 on the right. x1 is less than x2, but f of x1 is greater than f of x2, so the function's getting smaller. There's a third possibility we've already talked about. What happens right there? Increasing or decreasing? Neither, right. It has a horizontal tangent line. Ooh, tangent line. Hold on a second. Tom? What can you tell me about the tangent line to that increasing part of the graph, to this increasing graph? This one.
What do you mean then?
I'm not meaning anything. I'm just asking you a question. What can you tell me about the tangent line to this part of that increasing function?
It's also increasing. It's increasing.
The tangent line is increasing?
The slope of the tangent line. If you were like.
Okay, let's go there. The slope of the tangent line. What do you know about the slope of the tangent line?
It's positive on that line.
Everywhere here?
Except for at the ends. No?
Where it maybe levels off. But yeah. So you're saying the slope of the tangent line here is positive.
Yes.
And what about over here for the decreasing part of it?
It's negative.
Does everybody agree? Yes. Yeah. Okay, so then I ask everybody the question, is it possible to have a graph that's increasing at which the tangent line has a negative slope? No. So then can we generalize that? If a function is increasing, what do we know about the slope of the tangent line, Tom?
Positive.
And the slope of the tangent line is also known as the
Derivative.
derivative. So the derivative over here should be positive. The derivative over here should be negative. What about the derivative here?
Should be 0.
0. We've done this already, right? We've done that a ton. That's finding the critical number, so we don't care about that. We don't care about that. We just, I don't know where that came from. That's my sleeve, I think. We just care about these two guys. Okay? All right, pretty much Tom just did the whole lesson for you. Thank you, Tom. Let's give it up for Tom. But of course, life wouldn't be complete if I didn't include some calculus speak. So, that we already knew. Tom already explained that. It's going up, it's increasing. It's going down, it's decreasing. Again, stay with the logic here. Okay? This we just did. If f prime of x is greater than 0, the derivative is positive, then the function is increasing. If f prime of x is less than 0, then the function is decreasing. And then if it equals 0, we've done that already. It's a constant horizontal tangent line, possibly a maximum mean. We're not sure yet. We've got to deal with that in a second. Okay, so logically, is this all fitting together? We're good? Okay, again, don't worry about the calculus speak so much. We'll just make sure you understand what we're doing. And let's look at an example then of how we apply that. Here's a function. It's a cubic. I don't care what it looks like yet because I want to work on it without knowing what the function looks like. I'd like to figure out where that function is increasing and decreasing. Okay, to do that, you need to find the critical numbers first. So do that, please. Find the critical numbers. I picked an easy one to start. Maggie, what do you got for critical numbers?
0 and 3 halves.
0 and 3 halves? No. 0 and 1. Yes? Okay. Do I need to do that or are we okay? You forgot to multiply the 2 times the 3 halves, Maggie.
Oh, okay.
Okay. Well, I'm going to put it up here because we might need it later. 3x squared minus 2x. No, I lied. Minus 3x. Which is the same thing as 3x times x minus 1. So therefore, x is equal to 0 and 1 when this puppy equals 0. Okay. So those are critical numbers. Is the function increasing or decreasing at 0 and 1? It's a trick question. It's neither increasing nor decreasing at 0 and 1. What we care about are all the other numbers. So those two numbers split the graph into how many regions? 3, correct. So we care about those 3 regions. In those regions, each one of them will be increasing, decreasing, I should say, just say increasing or decreasing. And so keeping things organized is the difficulty here. And so in order to do that, I'm going to show you something called the first derivative number line. It looks like that. You draw a number line and you label it. The labeling is very important because it tells you a couple things. Number one, it tells you that it's a first derivative number line, but it also tells you where we're going to plug and chug. Gesundheit. Is that cough or sneeze? Sneeze. Gesundheit. Yeah. Okay, just want to make sure. It's awkward when you say Gesundheit to somebody who doesn't cough. Or it wasn't a snow, was it? Gesundheit? Not Gesundheit. That's not German for good life. That's the division thing. Okay, so we start with the number line. On the number line, put your critical numbers. The following statement seems silly. However, people make this mistake all the time. Please put them on the number line in the correct numerical order.
Knowing me.
0 goes to the left of 1. Now we have 3 regions to test. So our function was 3x times x minus 1 equals f prime of x. The reason this is here is because, like I said, first of all, it tells you the first derivative number line, but it also tells you where we're going to plug values into. You could go back to the original function, or sorry, the original derivative, but I find it easier if you look at the factored form. What I don't care about is the value. What I care about is the sign. So, Sedona, what number would you like to test to the left of 0? Negative 1 works just fine. What other numbers could you test? Negative? Negative 2. If you wanted to get crazy, you could do? Negative 3. You bad man, you. We could even do like a negative gabillion, right? So I don't care about the value. All I care about is whether it's positive or negative. Because as we talked about earlier, if it's positive, it's increasing. If it's negative, it's decreasing. So let's take negative 1. If I put negative 1 here, I get a negative number. Because negative 1 times 3 is negative 3. If I put negative 1 in here, I get a negative number. A negative times a negative is positive. The way you indicate that on your number line is you draw an upwards arrow. Positive goes below the line, the arrow goes above the line. So don't know what number would you like to pick between 0 and 1? Half is perfect. That's a half times 3, which is a positive number. 1/2 minus 1 is a negative number. Positive times a negative is negative. Whoop. Downward arrow. Okay, Sedona, last time. Pick something crazy over on the right. That's pretty crazy. It's not necessarily to the right of 1, but... Did you say why?
Yeah, why?
Are you asking me?
Yeah,
Why do you want something crazy?
yeah. Like,
Just take you out of your comfort zone? Live on the edge? I thought you meant the letter Y.
yeah.
That's what I was trying to be like, what are you talking about?
3,000.
3,000?
Yeah.
Whoa. All right. I can work with that. 3,000 is a positive times a positive, which is positive. Good to go. First common mistake with first derivative number lines is people automatically get, well, they get one region and they automatically think it switches back and forth between positive, negative, and negative, positive, negative. It doesn't do that. You need to test every region. That little picture tells us a ton of information. First of all, we now know where the function is increasing. It's increasing from negative infinity to 0 and from 1 to infinity. It's decreasing from 0 to 1. By the way, if you were, let's say I asked you for the decreasing region. Would you answer this way or this way? First way? Does everybody agree?
Yeah.
You would not include the point 0 and 1?
No.
Okay. Then we'll go with the first way. Works for me. What else does that picture tell you? Yes, we'll use that later. Anything else? What happens at 0?
Turning point.
It's a turning point. And you said a max?
I don't know, just turning point in
It's
general,
a
but
max.
max, yeah.
Why a max?
Positive, negative.
Okay. Does that make logical sense to everybody? If you're walking up a hill, you're increasing up a hill, and then all of a sudden you're walking down the hill, that means you cross the top of the hill, also known as a max. Using that same logic, what happens at 1? It's a min, right? If you're walking down a hill, and then all of a sudden you're going up, you've hit the bottom of the valley. Does that make logical sense? Beautiful. All of that from this one little picture. We know where the critical numbers are. We know where it's increasing and decreasing. We know where the relative max and mins are now. Just by doing this little bit of work here. Turn it on, it works better. There we go. So, what you just summarized for me is, in fact, the first derivative test. The first derivative test allows us to do what we've been trying to do for the last couple of days, and that is determine which of these critical numbers are maxima, which of these critical numbers are minima. And we're going to use that first derivative number line to answer the question, but there is a little snafu in there, which I'll get to in a second. Okay, so there's the function, in case you're wondering. That's what it looks like. Great, we all got that information where it's increasing, decreasing, and increasing. It's a cubic like we thought. Excellent, let's move on. Okay, so the first derivative test says this, which is exactly what you just described to me. If you're going up, and then you start going down, you've hit a max. If you're going down and then you go up, you've hit a minimum. Now, instead of describing it as going up and going down, we're using increasing and decreasing. Instead of using increasing and decreasing, we're talking about the derivative, which is also the slope of the tangent line, which goes back to what Tom explained earlier. Case 3 is worth looking at very quickly. Case 3 is just saying, oh, what if it doesn't do either one of 1 and 2? Well, then it's just not a maximum or a minimum. It could be something weird could happen at a point that would cause it to not be a local extreme up. Okay, make sense? Good. More so than just about anything we've done, we're going to use the KISS method here. It will make your life a lot easier. So let's do an example together first. I'd like to find the relative maxima and minima for that matter. I'll do this one first, and then I've got another example that you can do on your own. Take the derivative. What do I do with that derivative? Set it equal to 0. Yes, you do need to know how to factor. Yes, you do need to know how to factor. Come on, Rita, you got this. There we go. Is that right? Those are my critical numbers. They might be maxima, they might be minima, they might be neither. So now we can use the first derivative number line to test that. Again, label your number line as the F prime number line. Which one goes to the left? 1 or negative 5/3? Okay, just checking. You could go back up to the original f prime, 3x squared plus 2x minus 5. I like to use the product of the binomials to check these numbers for ease. I think it's easier to do that because then I'm just looking at positive times positive, negative times negative, and positive times negative. Christian, what number do you want to test to the right of negative 5/3?
0. To the right of negative 5/3, yes.
Did I just say to the right of negative 5/3?
I thought you said to the right.
That's my fault, I'm sorry. What I meant to say was, Christian, what number to the left of negative 5/3 do you want to test? Negative 2. Okay? Is that to the right of negative 5/3?
To the left?
Is it to the left?
Yes.
Yes. Okay. I got it. Okay. L is this side. R is that side. Okay. Good. So if I put in negative 2, negative number times a negative number, positive, increasing. Okay. I'm going to try this. Christian, what number to the right of negative 5/3 would you like to use?
0.
0 is a good number. 0 is a good number. That would be positive times a negative, which is negative. It's decreasing. And then how about to the right of 1?
2.
2. Positive times positive, positive. Here it seems like I'm positive, negative, positive. It does just flip back and forth, but again, that doesn't always happen. Okay, Kate, what can you tell me about negative 5/3?
It's maximum,
Beautiful. And how about at 1?
minimum.
It's a minimum. Great. We also know where it's increasing and decreasing. So it would be nice if this is all we had to do, but for some reason, the College Board does not like first derivative number lines. So I'm going to continue to encourage you to use that, but what they require are sentences. I don't quite get this, but I don't run the College Board. So when in a problem like this where you're asked to find the relative extrema, you're going to have to end this problem with a sentence, or actually in this case 2 sentences. And those sentences explain why Kate knows that negative 5/3 is a max and why 1 is a min. Why are they? Let's do 1. How do you know 1 is a minimum?
Because it's decreasing and.
Say again, I'm sorry.
It decreases and then increases.
Perfect. Okay. It would be nice if that were enough. They don't like that. They want something like this. A relative min occurs at x equals negative 1. Where does it happen? Well, first of all, what is it? It's a minimum. Where does it happen? X equals 1. And why does it happen? Because f prime changes from negative to positive. Which is exactly what she said. We just put it into this nice sentence form. You're going to write so many sentences that it's just going to become second nature. What is it? It's a relative max. Where does it happen? X equals negative 5/3. Why is it a max? Because f prime changes from positive to negative. But again, that doesn't mean we're not going to use the first derivative number line. It's the best tool we have for solving these problems. They just don't like to recognize it. Because why would they want to make our lives easy? Okay, we good? Yeah? All right. Now you do 1. I purposely chose this for a couple of reasons. Number 1, the derivative is challenging. Number 2, finding the critical number is challenging. If you can get to that point, the rest of it is pretty easy. So go. See what happens. Hopefully by now you realize you got some product rule action going on there. Okay, good. You having fun yet?
No.
Oh, it's so much fun.
Thank you, Luca. I feel better now.
You're killing it. I mean.
Oh.
No, that's backwards.
You did the hard part.
X to the negative 2/3.
Oh, that's what, wait, am I supposed to say this was?
So what's 1/3
Ooh, that's a great question, which we'll have to explore in a second. So it looks like derivative's looking good.
Can I use a quad formula?
Okay, let's stop for a second. How many people found the critical numbers? Raise your hand. Half of them? You got one of the two? What are they? 0 and 2. Okay, so how did you get to that point? So a lot of the things that we've done already come into play in this problem. So you'll recall when we were simplifying when we were simplifying derivatives, one of the things I said is you want to always factor out the negative exponent, which seemed trivial at the time. Now it becomes relevant. Okay, so I'm gonna take this through from the beginning and show you how to get to the point where you need to be. So f prime of x is 1/3 x to the negative 2/3 times 8 minus x plus, nope, I lied, minus x to the 1/3. Yes? Okay, good. You could factor out now, but I found it easier to distribute 8/3 x to the negative 2/3 minus 1/3 x to the 1/3 minus x to the 1/3. Eight thirds x to the negative 2/3 minus 4/3 x to the 1/3. Negative 1/3 minus 1 is negative 4/3. Okay, so here's where the fun part comes about. I'm going to take out a 4/3 and an x. Do I take the negative 2/3 or the 1/3? Negative 2/3, the more negative value, which leaves me a 2 behind minus x. Now, why x? Divided by u. Right? Oh, I see. You're going the other way. Yeah. So remember, we talked about this before, but if I have x squared minus x, when I factor out an x, what I'm really doing is dividing x squared by x, which is x, and dividing x by x, which is 1. So we're dividing here. X to the 1/3 divided by x to the negative 2/3. You subtract the exponents. 1/3 minus negative 2/3 is x. Okay. Which gives me my critical numbers then of, they said before, 0 and 2. Okay, so that's the first challenge, finding the critical numbers. That has nothing to do with what we've done today. That's the stuff we've been doing the last couple of days. Take the derivative, set it equal to 0. Actually, I screwed up here. I should do this and show that I'm setting it equal to 0, otherwise the critical numbers are invalid. Okay, now we find the extrema, which means I need a number line. It's an f prime number line, 0, 2. Let's do negative 10. So again, I like to go to the product here. Let's talk about this stuff in blue, in the blue rectangle. What can you tell me about that function?
Squares it and then takes the cube root.
Okay. I could rewrite this the following way. So does it matter what I put in for x? If I put in a positive number, will that be positive or negative? Positive. If I put in a negative number, will that be positive or negative? Positive, because it's squared, yeah. So it doesn't matter what I put in here, this stuff is always going to be positive, so that'll make my life a little bit easier. So I plug in negative 10. That's a positive times a positive makes this region positive. It's increasing. 1 works well. I already know that that's positive. 2 minus 1 is 1. Ooh, positive. Ooh. Haven't seen that before. And a big honking number like 100, positive times a negative is negative. Ooh. All right. All right. Here we go. All right. Paige, what can you tell me about 2? What happens in 2?
It's a relative max.
Beautiful. You want to take a shot at the sentence? What is it? You just told me.
Okay, relative maximum.
It's a relative maximum at, where does it happen? X equals.
2.
Good, and why? Here's the tough part. How do you know it's a maximum?
Because it's going from negative and then down to positive.
Oh, the other way around, positive to negative.
Positive then.
Right, and then you get this from here. It's going from positive to negative. Okay, so here's the other thing. She almost did a perfect job except for one thing. Pronouns are really bad. You don't want to say things like it. Because what is it? Is it the function? Is it the derivative? Is it, you know what I mean? So when you say that, when you write your sentence, and even when you're writing explanations, stay away from pronouns. A relative max occurs at x equals 2 because f prime changes from positive to negative. Good. What happens at 0?
Just continues like
In what?
continuously positive.
So there's no change.
Yeah.
So is it increasing or decreasing at 0? What? Some people said increasing, some people said neither. Anybody decreasing? No, I can't tell anybody. Okay, so graph it. Graph the original function, see what it looks like. Because then I got some good and bad news for you once you look at that picture. By the way, by graph it I mean your calculator or decimals. Don't graph it by hand. No, graph the function, not the derivative.
It's loading. I use batteries. How about this bad boy? Paperboard prep from here. I forgot to tell my mom that I need one.
Okay, so
Get the sales rack and here I am.
now that you've seen the picture, what's happening at 0?
The slope is undefined.
Correct. The tangent line is vertical, therefore the slope is undefined. So we go back to the question, is it increasing or decreasing at 0? The correct answer was neither. Okay? It's not really doing anything at 0. So the good news, you can now do a problem like that. Here's the bad news. Question, sir?
How would you write that, like, in a sentence?
You wouldn't. Right, because it's only asking for relative extrema, since 0 is not a relative extrema, you don't have to deal with it. Okay? It's only going to be extrema if we see a change from positive to negative or negative to positive. When everything is said and done with this stuff that we're doing in chapter 3, by the end of this stuff, after I give you a couple more tools, you'll be able to draw those graphs by hand. I will give you enough techniques that you'll be able to draw a very accurate graph of a lot of functions. And not just functions like parabolas and cubics and that kind of stuff. We're talking weird things like that thing you're looking at now, or even weirder functions. But we're a long way away from there. Right now, we can figure out where it's increasing, we can figure out where it's decreasing, and we can figure out where the maxes and mins are. We still don't quite know how to deal with that zero, but I'll give you some more stuff to use later on. Okay? Got it? Questions? The process that we used here, you're going to repeat ad nauseum. Take the derivative, set it equal to 0, find the critical numbers, put the critical numbers on a first derivative number line, test regions, answer questions. Those questions will be, where is it increasing or decreasing, where are the relative maximums? That's a unit circle cake that somebody baked for me a couple of years ago.
Wait, someone made that?
Somebody made that for me, yeah.
birthday or just like
It was just for a treat day. It was their birthday, they brought in cake for everybody.
They just got a big donut.
Yeah, they had an accident on the way in and had